On behalf of Vice President Hsu and all of his staff in research and innovation, we appreciate the board's willingness to take time in their meetings to hear reports by Spartans on their various research activities. In recent years, it has become the practice to invite a student researcher to make the report at April. And today I have the great pleasure of introducing Emily Steffke. She's a senior from Beal City, Michigan, with a double major in neuroscience in the College of Natural Science and English in the College of Arts and Letters, and she also has a minor in music in piano. An Honors College member and a Goldwater Scholarship nominee, she has been an undergraduate researcher in the labs of Doctors A.J. Robison and Michelle Mazei-Robison in the Department of Physiology, where she studies the underpinnings of stress, depression, and addiction, a topic which she will address for you in a moment. However, I also want to give you a brief picture of her as a full member of the Spartan community. She's a student athlete on the cross-country team and on the track team, and she also free climbs with MSU Rock Climbing Club. And she has been active during her time in MSU in the leadership of the Tower Guards Sophomore Honor Society. She's volunteered in pediatrics at Sparrow Hospital. She's mentored elementary students through honors times too. And this summer, she's going to be leading teenagers on month-long backpacking treks in the Four Corner States through an experiential education program. Best of all, she's preparing her first research publication, and she intends to be with us again next year. So if Emily would come forward, please.
Hello, as they said, my name is Emily. I want to thank you for inviting me to speak today. I'm going to be telling you about my research here at Michigan State that I've done in the labs of Doctors A.J. Robison and Michelle Mazei-Robison on stress and how this is encoded in our brains. So I want to start out by asking you to reflect on how you're feeling today. Maybe you've had a great morning, but maybe you've experienced a bit of stress. Maybe like me, you couldn't find your umbrella or the traffic was bad. Stress is something that we experience every day, and it's part of our lives. And stress comes in different forms. Acute stress can actually help us to think better and perform better. For example, Matt McQuaid steps up to the three-point line against U of M under quite a bit of pressure, but overall, he's able to make the basket. You know, his cognitive performance has been enhanced because he's able to think very sharply with this minor amount of stress. However, chronic stress can be extremely debilitating and cause problems thinking, processing information, and can lead to depression. Depression is something that affects over 16 million Americans every year and costs our society over $50 billion in treatment costs as well as lost productivity. Normally, when we think about depression, we're thinking about the emotion-related symptoms, but depression also has cognitive symptoms. It causes people to have trouble paying attention, have trouble thinking through problems and making decisions. So what my lab is really interested in is how is it that stress can affect our ability to think? How is this encoded in the brain? What is changing? The structure in the brain that we think about when we're trying to get at the bottom of this question is the hippocampus. The hippocampus is a brain region that's known to be involved in learning and memory. And within the hippocampus, there is what we think of as a working memory loop. So there are different regions of the hippocampus that you can see here. And we're really interested in how the connections between these neurons in these different parts of the hippocampus are changing their connections under stress to cause changes in the way people think when they are severely stressed. So when we're thinking about this, we're thinking about changes in the connections between neurons called synapses. How does this work? Well, when one neuron is activated, it sends a signal down its long branching part that we call an axon. And it causes the release of particles called neurotransmitters onto another neuron. This other neuron has these structures that we call dendrites that are like the antennae of a neuron, and they can pick up these signals and cause that neuron to fire and can go and affect other neurons downstream. So these antennae, these dendrites, are specialized for picking up signals from other neurons. And what I'm really interested in is how the structure of these dendrites can be changed by stress. Dendritic spines are these small projections coming off of dendrites. If you zoom way in on a dendrite, you can see these little, almost brush-like projections coming off. These are dendritic spines. They can vary in their morphology, so their shape, and how dense they are. And we normally think of more spines as helping to facilitate memory, and spines that are mushroom-shaped, that are large, are optimized for acting as an antenna to pick up those signals. So what I'm interested in is how could stress be affecting the shape and number of dendritic spines? Well, there's a protein called SGK1 that we think could be a potential player in this. We know that SGK1 is involved in stress. It's increased in its expression in scenarios of acute stress, but PTSD patients actually show over an 80% decrease in the level of this protein. However, we also know that SGK1 is involved in learning and memory. If we artificially decrease the levels of SGK1 in mice, they have impaired memory. So it seems like some kind of change in SGK1 could possibly be involved in modulating the connections between neurons in stress. So how do we test this? Well, I looked at how changing SGK1 could affect dendritic spines using mouse models. We do a surgery to inject different forms of SGK1 into the brains of mice, specifically into their hippocampus. So we can inject a non-functional version, or we can overexpress SGK1. Then we sacrifice the mice, slice their brains, image these slices, and get nice pictures that we can analyze and look at how the dendritic spines are changing. So this is how it looks. These neurons here are glowing because they are expressing the different forms of SGK1. These are two different regions of the hippocampus that we looked at. And when we zoom in, you see these nice cell bodies, and these are the axons and dendrites coming out. And when we zoom in even more, you can see the dendrites and these little dots coming off, that those are the spines. Now, I use a computer program that helps to analyze the different shapes of these spines, as well as calculate the density of these spines. So I can see how mushroom spines, specifically, are changing in these different conditions. So what did I find? Well, in the CA1, one of the regions of the hippocampus, we found that non-functional SGK1, effectively decreasing SGK1 activity, actually caused an increase in dendritic spines. However, in the dentate gyrus, another region of the hippocampus, we actually found that overexpression, increasing SGK1, also increased dendritic spines. So this is really interesting. You would think perhaps maybe just one, it would be a unidirectional action of SGK1. However, we see that it's working differentially in these two different regions, which is really interesting, and perhaps helps to explain how SGK1 is differentially having effects in acute versus chronic stress. And also is important for thinking about some of the differential pathways that are responsible for encoding changes in learning and memory in these two different regions, because the way these pathways work are actually quite different. So we are currently writing a paper about these findings, and it's really exciting. We are very convinced that SGK1 could be an important target someday for treatment of cognitive-related impairment in people who experience severe stress or depression, perhaps allowing them to think better and more clearly, and perhaps even come out of their depression. So I just want to acknowledge my research mentors, Dr. A.J. Robison and Michelle Mazei-Robison. They have been amazing mentors. They're in the Department of Physiology, as well as the Neuroscience program, and some of my sources of funding for this research. Thank you.
Thank you.
Are there any questions for Emily?
Emily, when do you sleep?
I actually sleep a lot. That's my key to success. I'm not kidding. On the team, they tell us that we need to get 9.25 hours of sleep every night. I get 8 to 9, and that helps me go throughout the day, and then I just sleep at night.
I just have a comment. You were very impressive. Thank you so much for sharing what you've learned with us.
Of course. Thank you.
There are many people in this room who are stressed out. What can we do to preserve the health of these dendritic spines besides taking medications?
Mental activity is going to be your best way for preserving the integrity of your memory. So when we think about people developing dementia as they get older, people who are engaged in their communities, engaged in social interactions, all of that kind of stuff, they retain memory and retain the integrity of things like dendritic spines as they get older and as they move through stressful situations as well.
Have you seen any correlation between physical activity and the health of these dendritic spines?
I have not looked at that specifically in my research, but I am aware that physical activity can play a very large role in maintaining memory abilities as people get older. So definitely something I would recommend.
Thank you so much for all that you do.
Thank you.